The next uses category is offset and gain control. DACs are extensively used for this purpose to trim out offset or gain error in the main signal chain and form part of many systems calibration routines. One common example can be found within user-built power supply units, where the DAC is used to trim the supplies to an exact output value. DACs are frequently used in many signal chains across N application areas to compensate for offsets and gains. This slide illustrates one example of a potential approach to the removal of offset and gain errors from the system. Firstly, DAC1 is used to correct for offsets on the input signal that is fed to the amplifier. This method can be used to remove a small offset of a few millivolts. A DAC is used rather than a fixed reference level as it gives you the granularity to compensate for very small magnitude of offsets. DAC2 is used to adjust the gain through the amplifier with the combination of RF and R1 to set the actual coarse gain of the amplifier. The DAC then provides the fine gain adjustment to the signal passing through the amplifier. The more accurate the DAC, the more precise the gain control. This circuitry allows for precision offset and gain control of the system and can be recalibrated to compensate for errors due to temperature or lifetime drift. This example is another approach to offset adjustment. A typical example seen in data acquisition systems where there are multiple different sensor inputs which have varying output ranges, all fed to a single ADC. This technique effectively shifts the signal upwards to match the ADC input range. The DAC is used as it enables the flexibility to alter the magnitude of the correction if the same buffering network is used for adjusting different input signals. This enables the one set of signal conditioning circuitry to be reused. The DAC is potentially shifting the input signal up or down. So for example, if the sensor output is bipolar in nature, centered around 0, but there is a need to use a standard single-ended, single-supply ADC to read the outputs, the DAC in this configuration is used to convert the output to a unipolar signal. A digipot is also used to vary the resistance in the feedback loop, and thereby vary the gain of the amplification network. An example could be a thermocouple output on one input, which would be small in magnitude, of the order of microvolts per degree C, and the other signal could be a bipolar reference voltage of ±5 volts, both of which will need different offset and gain adjustment values to enable the one ADC to be used. Another example within a signal chain is an offset adjustment in signal generation, where a direct digital synthesized product might be used to provide a sine wave which is centered around 0 volts, and a bipolar DAC is used to shift the signal and provide a unipolar output. A bipolar DAC is used here as it provides users with the option to offset the signal in either direction, thereby providing greater flexibility. The last example for offset and gain control applications is a variable gain amplifier, and these can be found in many signal chains where they are used to amplify high-speed signals in communication and test and measurement applications where precision gain control is needed. The primary signal to be amplified is connected on the positive and negative inputs and gain within the VGA. The DAC output is just to adjust the gain of the amplifier circuit and so the primary signal passing through. The DAC sets the voltage level on the gain pin of a VGA. The DAC can be used in conjunction with a resistor network to increase the precision of the gain adjustment. As always, the accuracy of the DAC determines the accuracy of the gain control. Gain inputs are often bipolar in nature to enable amplification of both positive and negative swinging inputs to the VGA. In this case, the zero volt bias from the DAC is the no gain configuration. So what type of DACs are most suitable for offset and gain control? The nano DACs and low voltage single supply products for their versatility and number of options available. Some of these products, like the 805541A, offer the required resolution of up to 12 bits with fast settling times and precision, and trim feedback resistors. These resistors can be used to generate the bipolar swings with an external buffer. As many gain inputs are often bipolar in nature to enable amplification in both directions, the bipolar products are often used. For increased precision, there are DACs like the 85791 family offering up to 20-bit resolution, 1 LSB or less INL, and very low noise and drift performance. The 85790 family include reference buffers to further simplify the circuit design for precision applications. Time zero accuracy specifications are not necessarily critical, as the DAC output can be adjusted to compensate for inaccuracies in the gain control network. However, drift over time and temperature specifications are critical to the stability of the gain network. One important point to consider is the DAC output stability. How the DAC level is will depend on the number of specifications, with drift and noise being the dominant contributors, and also the level of the load being driven. Drift can be due to temperature, the DAC reference, or general lifetime changes in silicon. Drift can often be calibrated for, while noise tends to be more random in nature and depends on the bandwidth of the system. As seen in the application examples, there can be more than one DAC function in any signal chain. So there could be set point control, gain and offset adjustments, which mean a multi-channel DAC is often required. Depots can be used in these applications for varying the resistance in the feedback network.